Assalamu alaikum students. Today we are going to start another topic that is related to the tensors we already discussed, that is Diadics. That is topic related to the classical mechanics as we deal with the kinematics of bodies that are spherical or rotational or in motion in classical mechanics, and under that we discuss the different objects that have number of coordinates in 3 dimension and components of the tensors, component of the coordinates. Now that is tensors and diadics are related to each other. So we're going to start with the topic of classical mechanics. In under this we are going to discuss diadics. That is the course of classical mechanics PHY 509 for the BS 5th semester. Now, starting with the topic diadics, we're going to discuss the definition for diadics. In mathematics, specifically multilinear algebra, A dyadic or dyadic tensor is a second order tensor written in a notation that fits in with the vector algebra. As you know that the vectors are responsible for the discussion of the object's motion and three-dimensional rotation and translational motion. So the dyadics are responsible for the discussion and understanding of the uh, kinematics of the objects, and that are all also the tensor, but they are the second order tensors, and they are in very good collaboration with the vector algebra. Now, for the definition of dyad and the dyadic, in the symbolic representation, vector notation is not sufficient to treat the second order or a higher order tensor quantities such as stress and strain. Diadic symbol represents the second order quantities, just as vector symbols represents are for the first order tensor quantities. As the first order differentials are represented by the vectors, but the second order representation is different from the first order differential quantities. So there is the symbol from the vector quantities is different. A dyadic symbol is indicated by a two-sided arrow over a letter. There, if there is some designation of a letter, then above and below there is the vector. There is a two-sided arrow above and below. A dyad is defined as two vectors standing side by side and acting as a unit. It means that these two arrows represent the second order differential, so they are standing side by side and acting as a one unit. The quantity previously written as phi dyadic is equal to AB has meaning only when it operates on other quantities. A linear combination of dyad is called a dyadic. Any dyad can be written in the form of a dyadic by expressing any of the vectors A and B or both in terms of their components along the Cartesian axis x, y, z multiplied by the corresponding units I, j, k, or generally by a set of independent units ei into I is equal to 1, 2, 3, and so on. So uh, the quantity AB as written for the dyadic will have a meaning when this quantity AB operates on other quantities, and the single linear dyad is called a dyadic, and they are written with their Cartesian components and multiplied by their unit vectors, and their unit vectors are represented as a set of unit vectors that ei. So we can write that vectors as a dyadic is equal to summation I ai ei, that is equal to, that will become as a1 e1 plus a2 e2 and a3 e3 as for the three Cartesian coordinates with their unit vectors. For the B component, for the B dyadic, that is summation j bj ej, and the B dyadic is represented for the three Cartesian coordinates with their unit vectors b1 e1 plus b2 e2 plus b3 e3. Then if we are going to write uh, dyadic, then we're representing by 5 with the arrowhead on it with the two-sided arrow above it, and that is equal to AB, that is called a dyadic. So we write summation ij ai bj ei ej, and that will give the whole quantity for the dyadic as summation ij phi ij ei ej. Ei and ej are the unit vectors for along the x and y direction, x, y, or any coordinate. So for that we write as a1 b1 e1 e1 plus a1 b2 e1 e2 and plus a1 b3 e1 e3 plus a2 b1 e2 e1 plus a2 b2 e2 e2 plus a2 b3 e2 e3. So now for the third coordinate, that is a3 b1 e3 e1 and a3 b2 e3 e2 and plus A3, B3, E3 and E3. That are all the components of the coordinates in the XYZ or three coordinate Cartesian coordinates. Now to understand dyadics, we have an introduction to dyadics. Dyadics in their reciprocal coordinates. We will discuss the identity dyadic and what is a unit dyadic and item factor. Then the coordinate transformation of dyadics in reciprocal coordinates, and under this we are going to discuss the dyadic invariants. After that, the classification of dyadics, and there are different kinds of dyadics: the dyadics green function solution of non-homogeneous Helmholtz differential equations, and in the last we have some references. Now, starting with the Diredix introduction, we can write a Diadic D with the arrowhead on both sides. There is an arrow above that Diadic, and there is a double arrow on it. Has the property that scalar multiplication with a vector produces a vector. When we multiply a scalar with a vector, we get a vector. So, V vector dot Diadic and D Diadic dot V vector are two different vectors. A diadic is a second order tensor. A particular diadic can be obtained by placing two vectors side by side with neither a dot nor a cross between them, such as this: A vector, B vector. A particular diadic can be obtained by placing two vectors side by side. It means that it is a diadic. Now, we will not place a dot or not place a cross, and two vectors written side by side is a diadic. Now the general properties of diadic are written as below, that diadic conjugate is equal to A vector B vector side by side having whole conjugate, that is equal to B vector A vector, that is called the conjugate of the diadic. Then we have D diadic is equal to A vector into B vector plus B2 vector plus so on Bn vector, that is written as summation I A I B I vector. That is, the diadic is equal to sum of compatible diadics. The compatible diadics can be the sum of the diadics, and that is a complete diadic, and the ratio will be a complete diadic. Two vectors are side by side, and the resultant will also be a side by side vector. Now V vector dot D diadic is equal to V vector dot into diadic vectors A vector B vector, that is equal to V dot vector dot A in bracket into B vector, that is equal to D diadic conjugate dot V, and is not equal to A vector into B dot V, and that is equal to D diadic dot V. It means that the vector is equal to scalar product with the vector. Scalar product with the vector. Now for the cross product, we have V vector cross D diadic is equal to V vector cross into A diadic A vector B vector, that gives V cross A into B vector, that is not equal to A into B cross V, and that is equal to D diadic cross V. Diadic is equal to vector product with the vector, that is a vector product. As above is a dot product, so that is a scalar product, and below is a vector product, so there is a vector product with a vector. Now then we have a double dot product. We can write V vector dot diadic dot W vector, that is equal to V vector in dot into diadic A dot A vector B vector dot W vector, that can be represented as V dot A into B dot W, and that will be equivalent to V vector B proportionality A vector into W, that is a scalar, and that is called a double dot product. Now V into diadic cross V triple product, that is equal to V dot into A vector B vector cross W, that is V dot into B cross W, that is not equal to V cross D dot W, that is a vector double vector scalar product. That is a double vector scalar product, and they are not equivalent. Equal. So V cross D diadic cross W, that is equal to V vector cross into A diadic values A vector B vector cross W, that is equal to V cross A into B cross W, that is a diadic, and that is called a double vector product. Above was a vector scalar product, and here is a double vector product. Now, in under the introduction of dyadics, we move to the general properties of the dyadics, that are d dyadic, d1 dyadic dot d2 dyadic, that is equal to a1 vector b1 vector dot into a2 b2 vector. So that gives a1 into b1 dot a2 bracket close b2 vector, that is a dyadic, and that is called scalar product of two diodes. Now d1 diode cross d2 diode, writing their dyadic values, a vector 1 b1 vector cross into a2 b2 a2 b2 vector, that is written as a1 vector into bracket b1 vector cross a2 vector into b2, that is a vector product of two diodes. Then we have v vector cross diode d1 dot d2 diode, that is equal to v vector cross into a, substituting the value we get v cross a1 bracket close into bracket b1 dot a2 into b2, and uh, that is dyadic triple scalar product of two vectors or two diodes. And similarly, this is another form is d1 diode dot d2 diode cross v, that is equal to a1 b1 dot a2 b2 cross v, that is written as a vector into b1 dot a2 into b2 cross v, that is also a triple scalar product of a vector and a two diodes. Now, moving to the next, diodes in reciprocal coordinates, we have a given diode AI is equal to AI J EJ into bracket is equal to a summation J AI J into EJ, that is equal to AI EI 1, that is equal to summation I A1 EI 1. So similarly for bi, that is bi k e k into, that is in the bracket summation k bi e k k, and that is equal to bi e m e m, that is equal to summation m bi e m e m. Now diode is equal to ai bi, that is equal to ai j bi k e j e k, that is equal to d j k e j e k. Here d j k is equal to a I j b I j, and that is equal to summation I a I j b I k. That is after solution, here we give a I j b I m a e j e m, where m approaches to k, so that gives d j k e j e k, that is e I j b I k, and then e a I j b I k e E J E K L, sorry, E L E K, that is approaches J, that is G K E J E K, where D J K is A I J B I K, that is equal to summation I A I J B I K. So we are using here the unit vector EM, that is equal to GMK EK. GMK is EM dot EK, GMK is EM dot EK, E power M dot EK is del mk, and gmk g power mk gk in gkg, that in subscript, that is del mj. We obtain djk is equal to m gmk dj m, that is equal to gij dik is equal to gij gkm dm, that are interchangeable, so that is equal to dlm is equal to glj phi jm is equal to gmk dik, that is equal to gij gmk dij, where gij gmk is convertible, so we write with the front and back arrow. As now another value is given as ai is equal to aij ej, and in bracket that is equal to summation j a I j e j, that is equal to a I e l e1 l is equal to summation I a I j e j1, that is equal to b j is equal to b, then b I b j k is e k, that is equal to summation k b I k e k, that is equal to b I e m b I m e m is equal to summation m into b I m e m. and the diode is equal to AIBI. So we write the values and write their vector forms and multiply. We get the resultant on the right hand side, that is equal to E1, E2, E3 in a bracket, then diode D, and then the column, in the column we have E1, E2 and E3. The conjugate of D, diadic of D is D conjugate is equal to BI. AI is equal to, writing the values for their conjugate, we have the similar value, that is E1, E2, E3, and D diadic transpose is equal to E1, E2, E3. Now decomposition of diadic in asymmetric and antisymmetric pairs, we have D diadic is equal to 1 over 2 D diadic plus D diadic conjugate, and plus 1 over 2 D diadic minus D diadic conjugate. The first term is the symmetric and second term is the antisymmetric. So we get the resultant as phi diadic plus omega diadic, and these two values are written as 1 over 2 E1, E2, E3 in the their component form D11 plus D11, D12 plus D2, D21. All the values are written, that is the value for the 1 over 2 D diadic plus D diadic transpose, and plus the second value, and all the components are written as, the second is for the 1 by 2 D diadic minus D transpose. Now the identity diadic, diadic or item factor, that is phi jk is equal to del jk, that is 1 or 0. When 1 is when j is equal to k, and 0 is when j is not equal to k. So the Diadic is equal to E1 plus E2 e power 2 plus E3 is equal to E1 plus E2 plus E3 is equal to, we write in a component form, we write in a matrix form. We have E1, E2, E3, and we have a unit matrix, and then the column, in column E1, E2, E3. So we have V vector dot diadic is equal, diadic I is equal to diadic I dot V. Writing the value and solving them, we get a V vector. We have used by using EM is equal to GMK EK. GMK is equal to EM dot EK, and GMK is equal to EM dot EK, and E power M dot EK is equal to del MK, and GMK GKJ is equal to del M. So we obtain the diadic I, and that is equal to Gij e power j, where Gij is equal to del Ij, and Gi power is equal to del Ij. Now the two diadics are taken the dot product, and the resultant is Dij k d2 k ej em. And when we take a dot product of two diadics D and I, we have a resultant D diadic. And when we take a dot product of diadic I to dot D diadic, there we again get a D diadic. So and I diadic dot I diadic, that is equal to I diadic. So we obtain also I diadic I proportional to I, that is equal to del Ij Ej proportional Ek Em is equal to del Ij del Km into Ei dot Ek into Em dot Ej, that gives del Ij del Km del Ij Ik del Jm, and that gives 1 plus 1 plus 1, that is a quantity 3. The values are written below. 1 have I is equal to j is equal to k, that is 1, and j I j k is equal to m is equal to 2, I j k is equal to m, that is equal to 3. So 1 plus 1 plus, every quantity have a 3 1 value, so all of them are added and we get a resultant of 3. Now for the identity diadic algebra, I diadic is equal to E1 subscript e power 1 plus E2 subscript e power 2 plus E subscript 3 e power 3 is equal to E1 e power 1 E1 plus E sub power 2 E2 plus E power 3 E3, and V dot I, that is equal to I dot V, that is equal to V vector, and D diadic dot I diadic, that is equal to I dot D diadic, that is D I dot I diadic dot I diadic is, that is I, and I proportional to I, that is 3. V vector dot I diadic dot W vector, that gives V dot I diadic bracket V dot W, that is equal to V dot W. V vector cross I diadic cross is equal to I diadic cross V vector, that is minus into V cross I diadic, I cross V into dot W, that is V cross I diadic dot W, that is equal to V cross W. I cross I diadic cross V dot diadic that is V cross I diadic dot D diadic that is equal to V cross D diadic into I cross D diadic dot to I diadic cross V that is equal to D diadic dot into V cross I diadic is equal to D diadic cross V, and I diadic cross into V cross V vector cross W vector that is W into V vector cross minus V vector into W vector. I diadic cross V into W into cross W minus W cross into I diadic cross V that is equal to V cross I diadic cross W minus W vector cross into V cross I diadic, that gives I diadic cross V into V vector cross W, and that this answer is equal to V vector cross V vector W vector minus W vector V vector. Now we're going to start the coordinate transformation of Diadics in reciprocal coordinates. Diadic is equal to AI BI, that is equal to its components, and that is equal to djk ejk, and that is equal to djk ej ek is equal to djk ejk. Let's find the relation between djk defined basis and ei and ei power to dmn defined in the basis of fi and fi. We have Diadic AIBA that is equal to DMN FM Fn is equal to D power M subscript N into FM F power N is equal to DMN FM Fn is equal to DMN FM Fn, where Fi is equal to alpha ij ej and alpha ij is equal to Fi dot Ei, that are written in matrix form, that is equal to L into L matrix into Ei E2 E3, and Fj is equal to beta Mj Em beta jk alpha ik is equal to del ij, and in matrix on that is equal to L minus 1 power transpose into E1 E2 and E3, and that the diadic is after solution gives djk is equal to dmn am jbkn, and all the components after solution give d power m subscript n is equal to d j k b n k a j m. We have the values of fi and fij, and in metric form writing and taking the solution that gives L into E1 E2 E3, where fj and bjk alpha jk that is equal to L minus 1 transpose E1 power 1 E power 2 E power 3, and we found the answer after solution d diadic is equal to matrix of D is equal to all the components a1 alpha 1 a1 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 2 a1 3 and d1 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 1 d1 2 d1 3 b1 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 b2 so on, and all the solution gives mod of L and d of mod of L and d mod of D and into mod of L power minus 1. Diadic invariants. Any diadic has 5 important invariants associated with their with 3 scalar invariants, 1 diadic invariant and 1 vector invariant. We found that under a coordinate transformation, f mod is equal to L into E mod, that is proportional to D diadic is equal to L mod D L power L mod power minus 1. The invariants of the diadics are derived from the following invariant equation, that is determinant mod of lambda I 3 cross 3 minus d mod, that is equal to det mod lambda I 3 cross 3 minus L mod d mod L power minus 1 is equal to det into determinant to L mod into lambda I 3 cross 3 minus d mod bracket close into L power minus 1, and that after solution gives that is equal to 0. This is the invariant characteristic equation right from the diadic, and that is equal to the determinant lambda minus d11 minus d12 minus d13 and all the quantities written, and after expanding we solve it and it gives a 0 answer. We found the 3 scalar invariants of the diadic, that is I1 I2 I3. All the values are written here. Now we have the classification of the Diadics. Physically, Diadics describe that each point the properties of the field that relate an input or cause a vector to an output or effect vector. If the family of input vector includes all magnitudes and directions, then one class of Diadics produces families of output vectors that also include all magnitudes and directions. Diadics of this class are called complete, all others are called incomplete. Accordingly, we can classify the Diadics as follows. The first is property is that mod of d is equal to I3 is not equal to 0. The three rows columns of d mod are linearly independent, that is complete. If that d mod is equal to I3 is equal to 0 and d diadic adjoint is not equal to 0 diadic, only two rows or columns of d mod are linearly independent, that is planar. If that d mod is equal to I3 is equal to 0 and d diadic adjoint is equal to 0 diadic, that is the three rows columns of d mod are linearly independent, that is linear. A planar diadic can be reduced by a suitable coordinate transformation to the sum of two diodes no less not less than 2, and d diode is equal to a1 b1 plus a2 b2. A linear diadic can be reduced by a suitable coordinate transformation to the single diode, that is d diadic is equal to a1 b1. Now the differentiation dialectics. Suppose we have a dialectic dt and the vector vt and that are differentiable functions of the parameter scalar t. Define u vector t ut proportionality vt dot dt is equal to vt into dot into a tbt, and wt is equal to proportional is equal to d mod t dot vt is equal to atbt dot vt, and differential will be written as du over dt is equal to dv over dt dot into a vector b vector plus v dot into da over dt b vector plus v vector dot into a db over dt is equal to dv over dt dot d diode plus v vector dot d diode d differential of diode with respect to time, where d diode over dt is equal to equivalent to d over dt into b plus a vector into db over dt. So dw divided by dt is equal to ab dot dv over dt plus ada over dt into b dot v plus a db over dt dot v plus d diadic dot dv over dt plus d diadic over dt dot v. Product rule is applied and answer is given. So d by dt into v dot d diadic is equal to dv over dt dot d diadic plus v dot d diadic over dt, and d by dt into d diadic dot v is equal to d diadic dv over dt plus d diadic over dt dot v. In the same way, d by dt into v cross d diadic is equal to dv over dt cross d diadic plus v vector cross into d diadic over d, and d by dt into d cross v d diadic cross v is equal to d diadic cross dv over dt plus d diadic over dt is cross v. Now the differentiation dialectics. Suppose we have a dialectic dt and the vector vt and that are differentiable functions of the parameter scalar t. Define u vector t ut proportionality vt dot dt is equal to vt into dot into a tbt, and wt is equal to proportional is equal to d mod t dot vt is equal to atbt dot vt, and differential will be written as du over dt is equal to dv over dt dot into a vector b vector plus v dot into da over dt b vector plus v vector dot into a db over dt is equal to dv over dt dot d diode plus v vector dot d diode d differential of diode with respect to time, where d diode over dt is equal to equivalent to d over dt into b plus a vector into db over dt. So dw divided by dt is equal to ab dot dv over dt plus ada over dt into b dot v plus a db over dt dot v plus d diadic dot dv over dt plus d diadic over dt dot v. Product rule is applied and answer is given. So d by dt into v dot d diadic is equal to dv over dt dot d diadic plus v dot d diadic over dt, and d by dt into d diadic dot v is equal to d diadic dv over dt plus d diadic over dt dot v. In the same way, d by dt into v cross d diadic is equal to dv over dt cross d diadic plus v vector cross into d diadic over d, and d by dt into d cross v Diadic cross V is equal to Diadic cross dV over dt plus Diadic over dt is cross V. Now the differentiation of Diadics under differentiation Diadics, gradient of a vector v vector in x y z, where del v is equal to 1x partial over partial x plus partial 1y partial over partial y plus 1z partial over partial z into vx 1x plus vy 1y vector plus vz 1z vector, that gives 1x vector 1y vector 1z vector in a row, and the matrix is written partial vx over partial x, partial vy over partial x, partial vz over partial x, partial vx over partial y, partial vy over partial y, partial vx over partial vz over partial y, partial vx over partial z, partial vy over partial z, partial z over partial z, and into column 1x 1y 1z, and this is a dyadic. Let compute, we have gradient v is compute conjugate is equal to v1x plus vy 1y plus vz 1z into the operator value is equal to the same as before, so it means that they are equal. Now the differentiation of Diadics under differentiation Diadics, gradient of a vector v vector in x y z, where del v is equal to 1x partial over partial x plus partial 1y partial over partial y plus 1z partial over partial z into vx 1x plus vy 1y vector plus vz 1z vector, that gives 1x vector 1y vector 1z vector in a row, and the matrix is written partial vx over partial x, partial vy over partial x, partial vz over partial x, partial vx over partial y, partial vy over partial y, partial vz over partial y, partial vx over partial z, partial vy over partial z, partial z over partial z, and into column 1x 1y 1z, and this is a dyadic. Let compute, we have gradient v is compute conjugate is equal to v1x plus vy 1y plus vz 1z into the operator value is equal to the same as before, so it means that they are equal. Now the dyadic identity summary: a dot into b cross c dyadic is equal to minus b vector dot into a cross d c dyadic is equal to a cross b dot c dyadic, and second one is a cross into b cross c dyadic is equal to b dot into a cross c dyadic minus a dot b into c dyadic, and a dot c dyadic is equal to c dyadic transpose dot a cross c dyadic is equal to minus into dyadic transpose cross a into whole transpose c dyadic transpose dot a into cross b dyadic is equal to minus into a cross c dyadic whole transpose dot b dyadic, del dot into phi into c dyadic, that is a scalar quantity, that is a phi del phi dot c dyadic plus c del dot c dyadic del cross into phi c dyadic is equal to del phi cross c dyadic plus phi del cross c dyadic, and second last is del cross into del cross c dyadic is equal to del into del dot c dyadic minus del square c dyadic, and the last is del dot del cross c dyadic is equal to that is like a Laplacian operator we study in the vectors.
Tensor analysis, like vector analysis, this tensor analysis has also two parts, or you can say that tensor analysis may be divided in two parts. First one is just tensor algebra, and the second one is tensor calculus. In fact, in this course on our tensor analysis, we will see the concepts of both tensor algebra and tensor calculus. So first of all, we will look to the tensor algebra, and after that we will see tensor calculus. But this is, as you know, this is our first lecture on this tensor analysis. So in this first lecture, I would just like to introduce you with tensors. So you can say this is just a brief introduction regarding the tensor analysis. So let us start to know about the tensor in brief, just as an introduction. And so I would like to start this tensor analysis by a basic, or you can say the fundamental postulate of physics. You know that a fundamental postulate of physics is that the laws of nature be expressed in equations that are valid for all coordinate systems, or you may say all reference frames. In an alternative way, you can say that the laws of nature or laws of physics are covariant or invariant. When you say that laws of physics are covariant or invariant, what does it mean? It means actually that these laws have the same forms in all coordinate system or all reference frames. You have also studied special relativity. This is just one of the postulate of special relativity, or you can say this is the basic postulate of our physics. In fact, a systematic method of investigating the behavior of quantities that undergoes coordinate transformation is the subject matter of tensor analysis. And as I have told you that we will see that there are two parts of tensor analysis, tensor algebra and tensor calculus. So actually when we say that tensor analysis, this is nothing, this is simply the generalization of vector analysis. We will see later on that the quantities like scalar, vector, dyadic, triadic, all are tensors of different rank or different orders. So people simply says that tensor analysis is simply the generalization of vector analysis. In fact, this tensor algebra and tensor calculus are needed for a better understanding of the tensorial representation of mechanics, electromagnetic theory, special theory of relativity, general theory of relativity, and the other branches of physics too. In fact, this tensor analysis became very popular when Einstein used this tensor analysis in developing the mathematical theory of his general theory of relativity. So after the advent of general theory of relativity, it was proved that this tensor analysis is indispensable, or it is essential for the treatment of general theory of relativity. And so after that this branch of mathematics becomes very popular, and its use in different branches of physics, as I have told you earlier, where was actually started. Now we will see some of the historical account regarding this tensor analysis. In fact, this concept of tensor was uh, appeared in the mathematics, or you can say physics, just by chance. The mathematician like Gauss, Riemann and Christoffel introduced the concept of a tensor, but their aim was not to give the idea of tensor. In fact, they were developing the mathematical subject of absolute differential geometry, but in course of the development of mathematical subject of absolute differential geometry, the concept of tensor came into the picture. So you can say that this concept of tensor was introduced in the mathematics just by chance. In fact, the subject of absolute tensor calculus, or you can say the tensor uh, analysis, was introduced by two famous mathematicians, Ricci and his student Levi Civita. In fact, first of all, these two mathematicians introduced the tensor calculus as an absolute subject, And as I have told you that Einstein made the use of tensor calculus in the mathematical development of his theory of his general theory of relativity. So after after the use of tensor in general theory of relativity, this subject became very popular in mathematics. And now today we see its use in several branches of physics and engineering. So this is actually the some of the basic historical account regarding the tensor. Now in this introduction, I would like to introduce you with tensor, that is what is how we can define this tensor. As I have told you earlier that this tensor analysis is nothing, this is simply the generalization of vector analysis. So what type of quantities are called tensor, we will see just as a definition. And after that, giving this proper definition, I will explain it by a proper example. There may be several examples, but in this lecture I would like to give only one example, and after that example you will have a concrete idea that what is a tensor. In fact, when you say tensor, actually tensor consists of a set of quantities, and those set of quantities are known as components of the tensor. And the properties of the components of tensor are independent of coordinate system. When you try to describe the components of a tensor in a particular coordinate system, the coordinate system does not matter. Its property remains invariant in all coordinate system. And if you know the components of a tensor in one coordinate system or in one reference frame, then there are certain laws of transformation by use of which you will see later that we can easily find what will be those quantities in another coordinate system. So these components of a tensor are related in two coordinate system are related by transformation laws. When we will discuss particular type of tensor in the forthcoming lecture, then you will see always a particular type of tensor is defined via a transformation law. So this transformation law is very important, and by the use of this transformation law, we relate the components of a tensor in two coordinate system, or you may say two reference frames. In fact, in a concrete manner, when you want to define the tensor, you can say that the tensors are objects whose components transform linearly and homogeneously under coordinate transformation. In this way, you can define tensors in a concrete manner. In fact, as I have told you that there is a fundamental or basic postulate of physics that the laws of physics or laws of nature are invariant under the transformation of coordinate system. And if you try to prove that the law that any given law of physics is invariant under frame transformation, then it becomes very easy to prove the invariance of laws if we express the law in tensorial form. In fact, in tensorial form of laws of physics, the invariance testing becomes very easy. You have studied the covariance or invariance of Maxwell's field equations in electrodynamics under the Lorentz transformation. Then you see that when we express the Maxwell's field equations in tensorial form, then it becomes very easy to prove that these Maxwell's field equations are invariant under Lorentz transformation. So whenever our aim is to prove the invariance or covariance of a physical law under transformation of frame, first of all, we express the particular law in tensorial form, and then we prove its invariance under frame transformation. Why? Because it becomes convenient in the tensorial form. The transformation or the invariance of the law under the frame transformation becomes very easy to explain. So this is the importance of tensor analysis. Whenever your aim is to test the invariance of a physical law, you must first of all express the law in tensorial form and then try to prove the invariance of that particular law. In fact, as I have told you earlier, that the tensor analysis is nothing, it is simply the generalization of vector analysis. So why? Why this tensor analysis was needed? You can see that in many physical problems, this vector notation is not sufficient to express the relation between quantities involved. It means you can say that this vector representation has a limitation. It does not give the correct result everywhere. For example, if you try to discuss the elastic property, the optical property, electrical property, and magnetic property, particularly of n-isotropic solids. N-isotropic. It means a solid whose properties depends on direction. Then you see that if the solid is isotropic, its optical property or electrical property or magnetic property in all directions are same. But if these properties depends on direction, it is different in different direction, then the solid is called anisotropic. And in case of anisotropic solids, it is not possible to discuss the properties in terms of vector analysis. Vector analysis becomes insufficient in dealing with the optical, elastic, electrical, and magnetic properties of anisotropic solids. So in this condition, we need the use of tensor analysis because vector analysis become insufficient in such situations. So you can say that in case of anisotropic solids, vector analysis, or you can say vector notation analysis, is not sufficient. And I have told you what is this anisotropic solid. Anisotropic solid, as I have told you, that the properties of such a solids depend on direction. Its optical property or electrical property or elastic property in different directions are different, and such solids are called anisotropic. And in case of anisotropic solids, the vector technique of explanation is not sufficient, it becomes insufficient. In fact, in this condition, the use of tensor concept is indispensable. So let us try to explain this fact by taking a proper example. Definitely you have studied Ohm's law. Actually, you know Ohm's law has two forms. You have studied in electricity Ohm's law, and you have seen that this Ohm's law has actually two forms. The first one is known as the scalar form, scalar or macroscopic form. Macroscopic form. In fact, when you express Coulomb's law in a scalar form or macroscopic form, what is the mathematical form of this law? This is expressed as V equal to IR. You know, V is actually the potential difference across a given specimen of the conductor. You can see this figure, and in fact I is the current flowing through it, and R is the resistance of this specimen of conductor. And this mathematical form of Ohm's law is known as a scalar form or macroscopic form. In fact, in this equation, you can see all the quantities are scalars. V, I, and R all are scalars. And macroscopic, it means these properties like V or I or R cannot be defined for a point. It is defined for the specimen as a whole. You simply say that current is flowing through the conductor. You never define current at a particular point. You say that potential difference across the conductor, not potential difference at a particular point. You also say the resistance of the specimen. If the shape and size of the specimen will change, this resistance will also change. So actually all these quantities are macroscopic quantities. So this form of Ohm's law, defined as V equal to IR, is known as a scalar form of Ohm's law or macroscopic form of Ohm's law. But apart from this, Ohm's law has a vector form, or you also call it microscopic form. Vector form of Ohm's law. Vector form or microscopic form. Microscopic form. And you have definitely an idea of this microscopic or vector form of Ohm's law. You know, this law is expressed as J equal to sigma times E, where you know this J is in fact current density vector. This is just a vector quantity. Current density vector. And E is electric field vector. This is electric field vector. And sigma, you know, this is electrical conductivity of the material of our specimen or conductor. Electrical conductivity. In fact, this form of Ohm's law is valid only when your solid is isotropic. So you can say that this form of Ohm's law, this is valid for which? Valid for isotropic solids or conductors, you can say. This vector form of Ohm's law holds when our conductor is isotropic. It means its electrical conductivity does not depend on direction. It is same in all direction. Then this vector form of Ohm's law holds, and so in nutshell you can say that vector form of Ohm's law can be used, but only when the conductor is isotropic. Now you know that in this case, if we want to express this equation 1 in a scalar form, then what will be the result? You can easily see. For that, let us express the vector quantity in terms of their components. So you know this vector J can be expressed as Jx I hat plus Jy j hat plus Jz k hat. Here actually this Jx, Jy and Jz, these are x, y and z components of the current density vector J. Or at the place of Jx, Jy, Jz, you may also write it like J1I plus J2J plus J3K. In fact, instead of the subscript x, y, z, here I have used the subscript 1, 2 and 3 for convenience. And again you can see The electric field vector like that can be written as EXI plus EYJ plus EZK. And similarly, instead of XYZ, for convenience, we write it as E1I plus E2J plus E3K. You can write it. So, in case of isotropic solid, you can express this Ohm's law defined in equation 1 in this way. At the place of J, we will write here J1I plus J2J plus J3K. And as the solid is isotropic, so in this condition, this sigma is just a scalar quantity and it has a constant value. It does not depend on direction or on point. If the material is suppose isotropic, at each and every point this quantity sigma has a unique value. So we will simply write here sigma, and instead of E, now write E1I plus E2J plus E3K. Now you know if two vectors are equal, then the corresponding components of the vectors are equal. So it means the x component of the vector in LHS will be simply equal to the x component of vector in RHS. Similarly, the y component of vector in LHS will be equal to the y component of vector in RHS, and so on. So let us equate the x, y and z components of the vectors in LHS and RHS. You can see then we will have actually three scalar equations. J1 will be equal to sigma E1. J2 will be equal to sigma E2. And J3 will be equal to sigma E3. Say this is equation 2. Actually this is nothing. This is simply Ohm's law, but we have expressed this vector equation defined in equation 1 in terms of the three equivalent scalar equations. Now from this scalar form of this equation, you can mark one thing here. If I ask you that this quantity J1, which is actually the x component of the current density vector J, this J1 depends on what? You can see this J1 is just a J1, you can see J1 is just a function of E1. It means you can also say that the x component of the current density vector J1 is not a function of E2 and E3. It means x component of current density vector depends only on the x component of electric field vector. It is independent of the y and z component of the electric field vector. Similarly, you can see the y component of current density vector is depends only on the y component of electric field E2, and it is completely independent of x and z component. And similarly, this J3 is a function of E3 only. It is independent of E1 and E2. So if the solid is isotropic, in that condition J1 is a function of only E1, J2 is a function of only E2, and J3 is a function of only E3. And in this condition, this quantity sigma is actually a scalar quantity. But if the medium is not isotropic, actually this equation defined in 2 holds for the solids which are isotropic. But now let us consider that our solid is not isotropic, but it is anisotropic. So in case of in case of anisotropic conductors or solids or medium, you can say. In fact, it is seen that the if our conductor is anisotropic, then any of the component of current density vector depends not only on the sorry, only one component of electric field. So, if the solid is anisotropic, then actually any component of the current density vector depends on all the three components of electric field vector. Actually, there was some problem in my throat, so don't mind. So, you can say in case of anisotropic solid, this J1 will be actually a function of E1, E2 and E3, not only E1. And similarly, this relation will be also for J2 and J3. So in this condition, if you want to express the value of J1, J2 or J3, then you will see that J1 is actually linearly connected to this E1, E2 and E3. So we can write that linear relationship between the components of current density vector and the electric field vector. So in this case, you can express J1 like this. This J1 is written as sigma 11 E1 plus sigma 12 E2 plus sigma 13 E3. And similarly, J2 is equal to sigma 21 E1 plus sigma 22 E2 plus sigma 23 E3. And J3 is equal to sigma 31 E1 plus sigma 32 E2 plus sigma 33 E3. And this result holds in case of 3D space, the Euclidean 3D space, or you can say the ordinary three-dimensional space. The x, y and z components of the current density vector, that is J1, J2, J3, are linearly related to all the three components of electric field vector E1, E2, E3 by this linear relationship, you can see. So here you can see that the quantities sigma 1, 1, sigma 1, 2, sigma 1, 3 and so on, these are actually the 9 components of the electrical conductivity. And so these 9 components of, there will be 9 components of electrical conductivity if the solid is anisotropic. Although you have seen that this sigma has only one value or only one component, it behaves like a scalar in case of isotropic solid. But if the solid is anisotropic, then this sigma is not a scalar and it is also not a vector, because you know a vector in 3D space has only 3 components, but this sigma you can see here has actually 9 components. So this sigma is neither a scalar nor a vector. Actually, this quantity is called a tensor of second rank, or it is called a dyadic. So you can write the components of this sigma in matrix form. So in matrix form, we can write the components of this sigma like this: sigma ij, this will be sigma 1 1, sigma 1 2, sigma 1 3, 1 3, sigma 2 1, sigma 2 2, sigma 2 3, 2 3, sigma 3 1, sigma 3 2, sigma 3 3, 3 3. So you can see that this array of 9 elements is neither a scalar nor a vector, because you know in 3D space a scalar has only one component and a vector has 3 components, but this sigma you can see has actually 9 components. So this sigma in this condition is neither a scalar nor a vector. In fact, it is recognized as a tensor, or a tensor of, more specifically, you can say a tensor of second rank, which is also known as dyadic. So, sigma in case of an isotropic solid or conductor is a tensor of second rank, or it is called a dyadic. It is called a dyadic. So you can see that particularly when we discuss the electrical property for an isotropic solid, then we can see that the vector representation of Ohm's law is not sufficient to deal with the actual state of affairs. But in this condition, the electrical quantity, which is electrical conductivity sigma, is not a scalar as it was treated in case of the isotropic solid, but it has a different nature. In 3D space, it has 9 components. So we simply say that in this condition, this sigma is neither a scalar nor a vector. It is a quantity which is known as dyadic. In fact, these are actually the components of electrical conductivity tensor in 3D space. So a tensor of second rank has actually 9 components in 3D space. Actually, number of components of a tensor depends on the dimension of the space. Here I have considered the 3D space. So this is just an example of components of a tensor in 3D space, or particularly the second rank tensor. So in this way, you can see this tensor representation, or tensorial representation of quantities becomes very essential if we are talking about the electrical properties, optical properties, or elastic properties, in particularly in case of anisotropic solids. So this is just a brief introduction regarding this tensor. We will see later on, in fact, the physical quantities, scalars, vectors, dyadic, triadics, all are collectively known as tensors. It depends on the rank. When you say a scalar, what does it mean? A scalar is also a tensor. A scalar is also a tensor. This is called tensor of 0 rank. So a scalar is also a tensor. This is also called invariant, and its rank is 0. And when you say vector, that vector is also a tensor. This is actually a tensor of first rank. First rank. When you say dyadic, that is a tensor of second rank. So, in nutshell, you can say that all the quantities that may be a scalar vector or dyadic, triadic, but all are tensors of different ranks. And this is why we simply said that tensor analysis is the generalization of vector analysis. So I have just introduced you with tensor in this lecture. In the second lecture on this tensor analysis, we will again see some of the basic fundamentals so that your discussion on the proper theory on tensor analysis will become easier.
Tensors and diadics are related to each other, and we already know that tensors are the first order differentials and diadics are the second order differentials, and they are very important in the kinematics and rotational understanding of the objects for in the classical mechanics. These are the references you can follow to understand, and further. The application of tensor diadics is in the applied physics. That is very important. So we're going to move to the next in the next lecture. If there is any kind of question regarding the topic, you can ask in the physical class. Today's topic related to diadics is completed. Is any kind of difficulty we can discuss later. Thank you so much. Allah Hafiz.